Finally, we are at a stage where we can learn how heart is acting like a dipole. First of all, we will learn this concept from a small two-cell model. After this, we can learn how the heart dipole is formed in the frontal plane and the horizontal plane or transverse plane. Now try to understand how we can think of a dipole from a two-cell model. Let's say in case 1, we have two cells, cell A and B. Both cells are depolarized. Polarized means they are at the normal resting membrane potential. So resting membrane potential is inside negative and outside positive. So we can say both cells have outside is positive. So we have to focus on the outside charge. So in this case, if outside charge is positive and both are equal, so we can say there is no dipole is forming here. No dipole formation outside. In case of In second case, we can see cell A is depolarized. So depolarized means inside potential got positive. So there is no need to focus on the potentials. Okay, you should think of the charge outside charge. So whenever this cell is depolarized means its outside charge is negative, and if this cell is polarized means its outside charge is positive. So what is the direction of dipole? It is from negative charge to positive charge. So you have to think of the outside charge. So this is a negative charge, this is positive charge. So we can draw a vector or dipole vector like this in this direction. Let's say taking case 3, in which after whenever we can say if these are at different potentials, current will flow from here to here, and after a time, let's say this cell is also got depolarized and both cells are at a depolarized state. So again outside is negative and this is also negative, so again here there is no dipole formation. Now talking about the case 4, here cell A is started to repolarize, and when it getting repolarized, so it's again the charge outside is positive, and this cell is still at the depolarized state, so its charge outside is negative. So just to think of the charge outside the cell membrane. If there is a difference in the charge from one cell to another, just make a dipole. So here in this case dipole is something like this. So this is the dipole in case of two cells. So I think you have understood the concept of dipole from the two cell model. Now we will focus on the heart, how dipole is forming in case of heart. As we know, electrical activity starts in the atrium and it starts with the SA node. So let's say we will start first about the atrial dipoles. So what is happening? Initially, this atrium is, say this is at a polarized state. So polarized means charge outside the cell membrane is positive. So I am just writing marking the charge outside the membrane. So it is positive. So outside charge is positive. So there is, we can say there is no dipole formation in this stage. So in the polarized state, there is no dipole formation. This we will take a zero dipole, means this is a zero dipole. Nothing is there. Now let's say SA nodal cells generated an impulse, and because of that few cells got depolarized. So I will say these parts, let's say, got depolarized, and these parts are still in a polarized state. So what can you infer? A small dipole, this is a negative charge and here is the positive charge, a small dipole can form out. So we can write here also, this is the P vector, and this dipole gradually change like this, and after a time the left ventricle also got depolarized. So what will happen? This is also negative, this is also negative, and later on this is also getting depolarize. So at this time you can see the charge, the overall dipole is from negative to positive charge. Some this sort of direction we can think of. So actually what is happening, the dipole for the atrium starts and make a loop, and again after the whole it got depolarized, totally depolarized, all the negative charges come here, and again we come at a stage when there is no dipole. So we can just, I am marking a loop, this is called a p loop, and the vectors are moving like this is called the p loop for the atrial depolarization or vectors. Now coming on the ventricle side. So again, what is happening for a ventricle who is at a polarized state? It means all the charges are outside are positive. This is a polarized state of the ventricle. Means there is no dipole formation presently. No dipole. So just marking a dot here. Now after a time, when depolarization or impulse come in the septum, so first of all, the septal part of the left side will depolarize. So I can just make this left side is depolarized. Means outside charges are negative and inside charges are still positive. And the remaining ventricle is still at a polarized state. So we can think a small septal vector in this direction will form. So we can say this is the left side and this is the right side. So a small septal vector directed towards the right side is going to form in this stage during the septal depolarization. And gradually we have seen the impulse will move towards the anteroseptal side, and gradually it moves towards the base of the ventricles. So we can think, let's say कि depolarization is still going on. So what we can write, let's say कि this whole portion got depolarized, and we have seen depolarization starts from the endocardial towards the epicardial side. So epicardial region is still not depolarized. So something charge distribution, something of this sort will form. So we can think this is the negative center and outside is the positive center. So some vector something like this will form out. So in this way we can say the depolarization is still going on. So this is the depolarization is still going on. So this vector who initially was in this direction, gradually it was in this direction, it is increasing in this direction. If depolarization continues, we can say most of the ventricle got depolarized, but their bases are still at the polarized state. So we can say a vector points toward this side is there. So we can plot a vector. Initially this is the septal vector, and this is how the vector is going along with depolarization, and finally this vector comes out. So this is just forming a loop, something like this. I have make the wall of the left ventricle and right ventricle bit equal to just to make you understand the distribution of charges. Otherwise, the left right ventricle wall is very thin as compared to the left ventricular wall. Now we come at a stage when the whole ventricle got depolarized. Let's say it is depolarized. So what has happened? No dipole is formed here. So we got a loop something like this, where this is the septal vectors initially form, then the ventricle is forming these vectors, and finally again it comes to a 0 point when there is no dipole is there. So in this way we got a QRS vector loop that represents, this loop represents ventricular depolarization, ventricular depolarization. So once ventricular depolarization happens, now it's time for the repolarization. So if we can think, the cell who got depolarized first will repolarize first. So what should happen if suppose these are the vectors who got, these are the cells who depolarize later. Initial ones depolarized early, so I think this should be repolarized first. So vector should be from in this direction, but this is not actually happening. So this is not right. What is actually happening is this: the cells who depolarize later will repolarize first, and this is due to the shape of the cardiac potential, and that is due to some channels. Let's say this is the endocardial cells still in the depolarized state, though epicardial cells depolarize later, but they will repolarize first. And we can understand this with this cardiac potential. Let's say I am making the cardiac potential of endocardial cells, and it is something like this. This is the cardiac potential of endocardial cells. Now I am drawing the cardiac potential of epicardial cells, because epicardial cells depolarize later. They start to depolarize later. So I am making with some delay. They are started here, let's say, but they have started their repolarization early. And the shape of this cardiac potential is due to the potassium channels, some special type of potassium channels which has got different gating kinetics. So this is the reason that repolarization vector also is facing like this. So we can think this is a repolarization loop. So finally, and we can also call it T wave loop, because it will manifest as T wave in on ECG. So once repolarization happens, again it will come in the polarized state. So again there is no vector. So I hope you understand how the hard dipole vectors are forming because of the distribution of charges. So we can sum up, this is the p vector loop. So here vectors are forming in this way, and similarly this is the QRS vector loop. Vectors are forming, this is a septal vector, then vectors are forming in this way. And finally we can draw a T wave loop. This is the T wave loop. So we have P wave loop, QRS vector loop, and the T vector loop. So in this way we got a hard dipole vectors. As we have discussed about the hard dipole vectors over the frontal plane, the same can be think of for the transverse plane. And the majority of vectors are governed by the ventricular vectors. So the same happens when septum is depolarized, the vector will be in this position, and gradually it goes anteriorly, and gradually it will goes towards the positive sides. And all those vectors will soon, we will see, got projected on the leads and will form the ECG waveforms. Till now we have developed the concept of leads and also understand the concept of hard dipole vectors. Now we have a ground to understand the interaction of lead and the dipole, and we will learn how the ECG waveforms will originate. Thank you. Thanks for watching.